Hello and welcome to my YouTube channel Senan Academy. In today's lecture, we'll be discussing about magnetic materials and we'll draw BH curve of ferromagnetic material. We'll be covering the following topics. Number one is magnetic dipole. We'll understand how a magnetic dipole is formed and we'll discuss what is a magnetic dipole moment. And then we'll go to the different types of magnetic materials. We'll discuss their properties. Next is we'll discuss the domain theory of ferromagnetic material. After that, we'll draw the BH curve of ferromagnetic material and we'll discuss why this BH curve is also called as hysteresis loop. And in the last, we'll discuss the hysteresis loss. So let's start with the dipole moment. We know that every substance in this world consists of atom. Now, if we consider a very simple atom consisting of nucleus with a proton and an electron around the nucleus, and we know that this electron is in continuous motion around the nucleus. We know that the electron is a charged particle, and in this case a charged particle is in motion. So when a charged particle is in motion, it constitutes current. So we can consider, or we can say, that this motion of electron is equivalent to a loop of current, and that current will be flowing in opposite to the direction of motion of electron. So here the direction of motion of electron is clockwise, so the direction of current will be anti-clockwise. Now we will find, due to this loop of current, what will be the direction of magnetic field and where our north pole and south pole exists. Okay, consider a bar magnet. In that bar magnet, we know that the magnetic lines of force is from north pole to south pole outside the magnet, and from south pole to north pole inside the magnet. Now if you stand in front of north pole, you will find that the magnetic lines of force are coming outward perpendicularly to the surface of the magnet. And if you stand in front of south pole, you will find that the magnetic lines of force going perpendicularly inside the magnet. So just note these 2 points, that when you stand in front of north pole, you will find the magnetic lines of force are going out perpendicularly, and if you stand in front of south pole, you will notice that the magnetic lines of force are going inside perpendicularly. Now let us come to this loop of current. If you apply Maxwell's right hand thumb rule to find the direction of magnetic field due to this loop, you will find the magnetic lines of force are coming outward perpendicularly from the surface of the coil. So here the magnetic lines of force are coming outward perpendicularly from the surface of the coil, so we can consider, or this loop is equivalent to the north pole of the bar magnet. So we can say that this loop of current will behave as a north pole. Now if the direction of current is reversed, that the motion of the electron is reversed, or the direction of current is in clockwise direction, the loop of current will behave as a south pole. Now if you see here, the north pole, this loop of current is behaving as a north pole when the direction of current is anti-clockwise, and when it is in clockwise direction, it behaves as south pole. Now if you analyze this loop by seeing both the sides like this, and let us consider the direction of current is in anti-clockwise. By applying the Maxwell's right hand thumb rule, you will find the direction of magnetic field is from left to right. Now if you see the face, if you see this face, the face at the right side, at this face you will find the magnetic lines of force going outward perpendicularly. So this face of the coil will behave as a north pole. And if you see the face at the back side of this, that is at the left side, this face, at this face you will find the magnetic lines of force coming inward perpendicularly. So this side will behave as a south pole. It means a loop of current will not only behave as a single north and south pole, but it will behave as a dipole. It consists of north pole and south pole. Means if this is a north pole towards you, then the south pole will be at the back of this face. And if this face is south pole, at the back of this face will be north pole. Means north and south pole will exist together, and we know that north and south pole cannot exist individually. Independently, north pole and south pole cannot exist. Here also north pole and south pole are existing together. So this north pole and south pole will constitute a dipole. Now let us define a term called as magnetic dipole moment. Magnetic dipole moment is actually the measure of magnetic strength, and that magnetic dipole M represented by M, which is equal to number of turns of the coil multiplied by current flowing through the coil multiplied by the area of cross section of the coil. In this case we have only one turn loop, so N will be equal to 1. So magnetic dipole moment in this case will be equal to I into A. This magnetic dipole moment is a vector quantity. So the direction of magnetic dipole moment is from south pole to north pole. Now by this discussion we can say that dipole moment, that is magnetic dipole moment, exists in every substance. Since every substance is consist of atoms, so dipole moment exists in every substance. Now the dipole moment which we have just discussed is called as orbital dipole moment. This is the dipole moment which is because of the motion of the electron around the nucleus. There is another type of dipole moment present inside an atom, and that dipole moment is because of the spin of the electron on its axis. And the spin dipole moment, which is due to the spin of the electron, is stronger as compared to the orbital dipole moment. So later on we will see that in ferromagnetic materials this spin dipole moment is dominating. That is why our ferromagnetic material gets strongly magnetized when they are kept inside the magnetic field. Later on we will discuss this whole concept, that how a magnetic material gets magnetized. Now if dipole moment is there in every substance, then what are magnetic materials then? So let us conclude some of the points to discuss how could you define what is a magnetic material. Okay, we know that every substance contains magnetic dipole moment. We have just discussed it. Now these dipoles are arranged in different materials in random orders. And why they are arranged in random fashion? Because the atoms and molecules are arranged in random fashion. That is why all the dipoles in a material are arranged in a random fashion. Due to the random orientation of the dipole, some of the dipole moments cancel each other. In some material, the overall dipole moment will be 0. And in some of the material you will find we have a resultant dipole moment. We are talking about magnetic dipole moment. Okay, we are not talking about electrical dipole moment. So in some of the material we have some dipole moment, and some of the materials we don't have any dipole moment. It doesn't mean that that particular material does not have dipole moment inside it. They have, but the overall dipole moment will be 0 because the orientation is random. So it might be possible that they cancel each other. Now when magnetic field is applied to that particular material, the dipole tries to align themselves in the direction of applied magnet. A torque is developed, and that torque tries to rotate the dipole such that the dipole will occupy a place of a minimum energy in a magnetic field, and that is possible when the dipole moment is parallel with the magnetic field. So dipole actually tries to align itself in the direction of applied magnetic field. Now we'll see that how it happens. Now we'll show the dipole moment by an arrow, and that arrow head is representing north pole and arrow tail is representing south pole. Now let us place a dipole. This is a dipole in a magnetic field. We'll see what will happen. When you apply magnetic field, dipole tries to align itself in the direction of magnetic field. A torque will be developed on the dipole which rotates the dipole in the direction of magnetic field. Okay. Now take a material. Suppose this is a material in which the dipole moments are arranged in a random fashion. And let us consider, due to this arrangement of dipole, the total dipole moment or resultant dipole moment is 0. Now what will happen if we apply magnetic field? Let us see. If we apply magnetic field, dipole tries to align itself in the direction of applied magnetic field. Due to this particular substance will develop its own internal magnetic field. Now, this property of developing magnetic field inside the material, the magnetic materials are classified into 5 different categories. Number 1 is paramagnetic material. These are the materials which get weakly magnetized. This is what the meaning of magnetization. That when we place a magnetic material inside a magnetic field, the dipole tries to align itself in the direction of magnetic field. Due to this alignment, the material develops its own internal magnetic field, and that process is called as magnetization. So when a paramagnetic material is kept inside a magnetic field, it gets magnetized in the direction of applied magnetic field, but the magnetization is weak. So we can say that when we keep a paramagnetic material inside magnetic field, it will develop north and south pole in such a manner it will get attracted towards the magnet, that it will develop the opposite pole. It will develop the opposite poles. And the magnetization is not that much strong. They are weakly magnetized. Some of the examples are aluminium, manganese, platinum, etc. Now the next category is diamagnetic materials. They are also weakly magnetized, but they magnetized in the opposite direction of applied magnetic field. That is, when they are kept near a magnet, they will repel the magnet. Some of the examples are copper, phosphorus, antimony, etc. Now the next one, which is very important, we are going to discuss in more detail, that is ferromagnetic materials. They get strongly magnetized in the direction of applied magnetic field. They get attracted towards the magnet. We'll discuss why they get strongly magnetized, and we'll draw the BH curve for this ferromagnetic material also. Some of the examples are iron, nickel, cobalt, and their alloys, like alnico is one of the alloy which is a ferromagnetic material. Next one is antiferromagnetic material. They are also magnetized strongly, but they magnetize in the opposite direction to the applied magnetic field. And examples are chromium, nickel oxide, chromium oxide. And the last one is ferrimagnetic materials. Their property is very similar to the ferromagnetic materials, but they are not that much strongly magnetized when they are kept inside the magnetic field. Some of the examples like ferrites, like barium ferrite, magnetite is one of the example of ferrimagnetic materials. So now these are the 5 different types of magnetic materials classified based on how they get magnetized when they kept inside the magnetic field. Now we will discuss some more detail about this ferromagnetic materials. So the first thing which we are going to discuss about this ferromagnetic material is magnetic domain. So what is a magnetic domain? First we'll analyze the structure of a ferromagnetic material. Let us consider this is a ferromagnetic material, and this ferromagnetic material consists of obviously dipole moment. But in case of ferromagnetic material, the dipole moments are not arranged in random fashion, but the group of dipole moment, there are some group of dipole moments which are arranged in a same orientation. there are group of dipole moments which are arranged in a particular direction, and that group of dipole moment is actually called as magnetic domain. So we say that magnetic domains are randomly arranged in this case. We're not saying that the magnetic dipole moments are arranged in random fashion, because there are group of dipole moments which are arranged in a particular direction. So here we can say the magnetic domains are arranged in random fashion. Now let us consider, due to the random arrangement of magnetic domain, the resultant dipole moment of the material is 0. Now what will happen if you apply magnetic field? The time we apply magnetic field, the dipole tries to align itself in the direction of applied magnetic field. But now in this case, we will find this will develop a very strong dipole moment in the direction of applied magnetic field, because a group of dipole moments will now align themselves in the direction of applied magnetic field. So this will develop a strong magnetic field. That is why we say, because of the rotation of domain, this type of material gets strongly magnetized when it is kept inside the magnetic material. So let us define some of the terms related to the magnetic materials. The first one is magnetic domain, which is related to the ferromagnetic material. These are the group of dipoles arranged in a particular direction. Next one is spontaneous magnetization. This is the resultant dipole moment present when no external magnetic field is applied. So we have taken this was spontaneous magnetization as 0 in both the cases we discussed earlier. And the next one is magnetic susceptibility. It is the quantitative measure of the extent to which a material may be magnetized in relation to a given applied magnetic field. Mathematically, it can be represented as the magnetization M. It is the ratio of magnetization M to the magnetic field strength, and this magnetization is actually dipole moment per unit volume. So if you think about susceptibility of paramagnetic material, diamagnetic material and ferromagnetic material, you will find that magnetic susceptibility of paramagnetic material is small and positive, and for diamagnetic material it is also small but negative, because magnetization is in opposite direction. And in ferromagnetic material, it is magnetic susceptibility is large and positive. Okay, so these are some of the points related to the magnetic materials. Now our next task is to draw the BH curve. So we will now move towards the BH curve. Before drawing the BH curve, let us discuss some of the points related to how we can place a magnetic material inside a magnetic field. Let us take a magnetic material. Suppose this is a magnetic material just shown on screen. If you wrap a coil around it like this and apply voltage across the ends of the coil, a current starts flowing through the coil. Due to this current in the coil, a magnetic field will be developed. And this magnetic field, you can see, it actually passes through the magnetic material. So now we can consider this magnetic material is under the influence of magnetic field. And we know that the strength of magnetic field in this case is not constant, because it will be dependent upon current. This magnetic field strength we have already discussed in previous lectures, that it is equal to the ratio of mmf upon length of the path of the magnetic flux. Now here in this case, N and L are constant. So if N and L are constant, we can say that H is proportional to I. So as we change the current, the magnetic field strength will change. If we increase the value of current, strength will increase. If we decrease the value of current, strength of magnetic field will decrease. And now we will observe how the magnetic field of the material is changing by changing the value of current. Now due to the applied magnetic field, the magnetic dipole moment of the material tries to align themselves in the direction of applied magnetic field. So the material will develop its own magnetic field, and that magnetic field is called as magnetic flux density, and it is the ratio of magnetic flux divided by area of cross section. For a material, area of cross section is constant, so that magnetic field, the magnetic flux density will be proportional to the flux. Now in case of BH curve, we will find that how this B, internal magnetic field of the substance, is actually changing with respect to the applied magnetic field. So this is what we are going to draw BH curve. This B is internal magnetic field and H is applied magnetic field. Let us draw the BH curve. In this case, to draw the BH curve, we will take alternating current AC. In order to understand, by changing the current, the magnetic field is changing, so how that magnetic field is magnetic field of the material, internal magnetic field of the material is behaving. We'll see how that BH curve is drawn. Now let us draw the BH curve. As we know that by increasing the current, the H will increase. Now if the applied magnetic field increases, the strength of applied magnetic field increases in a magnetic material, what will happen? The more and more dipole tries to align itself in the direction of applied magnetic field, because the torque will increase. So B will increase linearly. But after some time, after say point this, what will happen? The increment of B is not very high, because after this point there will be very less amount of dipole left to align themselves in the direction of applied magnetic field. So the internal magnetic field, which is now increasing in linear order, after this it will not increase in that particular proportion. So this point, after this point, the magnetic material will not develop that much amount of magnetic field. So this point is called as point of saturation. Now the magnetic material is saturated. There are no more amount of magnetic dipole moments are left which can align themselves in the direction of applied magnetic field. So very less amount of dipole will be aligned themselves in the direction of applied magnetic field. So there will be very less increment in B. So this point is called as point of saturation. After this, the substance gets saturated. Now what will happen after this? When the current starts decreasing. Obviously, when current starts decreasing, the strength of magnetic field also decreases. But it has been observed in magnetic material, ferromagnetic material, that the de-alignment of magnetic dipole moment is not the same as the alignment. Means, if during the alignment, during the increment of H, the alignment of dipole moment is high, but de-alignment is not high, de-alignment is somewhat smaller. So we'll find that the BH curve will not follow the same path, but it will follow the another path like this. Now when the current is 0 at this point, but magnetic field of inside magnetic field of the material will not be 0. But that means it has got some kind of magnetic field inside it. Some of the dipoles are still in the direction of applied magnetic field. At this point where the magnetic field is left, this magnetic field is called as residual magnetism. Means even after the removal of applied magnetic field, that magnetic material will behave as a magnet. It has a permanent magnetic field inside it. That point is called as retentivity. So this is the residual magnetic field left after the removal of applied magnetic field. Now what will happen if we reverse the direction of applied magnetic field? That is, if the current is in reverse direction, this residual magnetic field now will go on decreasing, because the dipole now tries to align themselves in the direction of applied magnetic field, which is in the opposite direction now. So the resultant dipole moment now will be going to 0, and at some point in the opposite direction, at some point the value of residual magnetic field is now 0, and this point is called as coercivity. Coercivity is the amount of magnetic field required to make the residual magnetism to 0. Okay, now after this, if we continue increasing the applied magnetic field in the reverse direction, again it will follow the same path. The dipole tries to align themselves in the direction of applied magnetic field. Now it is in the opposite direction as before. So what will happen? Again, it will reach the point of saturation one time, and then after that there will be very less increment in B. So after this, material gets saturated in the opposite direction, and again if the H is again reduced, so it will follow not this path but other path, and that will be like this. And if it is continuous till if the H is again made 0 and reversed, then it will again come to the same point here. So this curve, BH curve, which we have just seen, is called as the hysteresis loop, and this is what BH curve of ferromagnetic material. So there are only 2 points to be noted here. One is what is the retentivity, and one is what is coercivity. Retentivity is the amount of, it is the ability of a magnetic material to retain magnetic field even after the removal of applied magnetic field. And what is coercivity? It is the amount of applied magnetic field required in opposite direction to make residual magnetism to 0. So these are 2 very important points of BH curve. Now we'll discuss one more important point related to BH curve. And what is that? That is, we have discussed these 2 points as retentivity and coercivity. Now we'll see what will happen at these 2 points. Let us consider these 2 points to be P and Q. At point P, we see that H is 0 but B is not 0. At this point, H becomes 0 but B is not 0. B have got some value, positive value. Now at point Q, we see that H is non-zero but B is 0. Means if you follow this path, we are seeing that B is becoming 0 after H. So if some quantity is getting 0 after some other quantity, so we can say that the quantity which gets 0 after some time is lagging the quantity which gets 0 before it. So we can say in this case B becomes 0 after H, so B lags H. Or we can say B hysteresis H. Hysteresis is a Greek word which means to lag behind. Okay, so we can say that B hysteresis H, and that is the only reason why this loop is also called as hysteresis loop. Since B lags H in this loop, so we say it is a hysteresis loop. It's a closed loop, it's a closed path. Okay, so that is why it is called as loop, and this loop is called as hysteresis loop because B lags H in this case. Now the last point we are going to discuss now is what is hysteresis loss. It is very interesting to discuss what is hysteresis loss. Now we have seen that when we apply magnetic field, the dipole tries to align itself in the direction of applied magnetic field in a ferromagnetic material. Now let us take a ferromagnetic material and a dipole moment. Let us take only one dipole moment in order to see how this dipole moment is actually responding with respect to the applied magnetic field. Okay, we are applying magnetic field on this. Okay, and that magnetic field is dependent on current, which is alternating current. Now we will see what will happen if we apply magnetic field to the dipole. Okay, now as the magnetic field increases, the dipole tries to align itself in the direction of applied magnetic field. Now you can see, just observe the motion of the dipole, how it is moving by the application of applied magnetic field. You can observe then when the current increases, it gets aligned in the direction of applied magnetic field. When it is decreases, it's again de-align itself. And when the direction of applied magnetic field reverses, it again tries to align itself in the opposite direction to the applied magnetic field, and again when it is decreases, it de-align itself in the direction of applied magnetic field. So this continuous motion of dipole aligning and de-alignment is actually consuming some energy. It is the continuous process. So this alignment and de-alignment, due to the alignment and de-alignment, it consumes some energy, and this energy which is consumed by the dipole moments is actually being wasted. There is no use of this energy, so it's a loss of energy. So this energy which is being lost inside the material due to the alignment and de-alignment of dipole moment is actually called as hysteresis loss, and this hysteresis loss is proportional to the area of the loop. In the coming lectures, we'll be discuss about the mathematical expression of hysteresis loss and some other loss related to the iron materials or ferromagnetic materials. So this is all for now, and thanks for watching my videos.